Yes,
Okay.
recording has started. Yeah, please start.
Yeah. Yeah. Sure. Okay. Yes. So, Srikanth Tamilselvam, sir, he is a senior technical staff member at IBM Research Labs India, where he drives innovation at the intersection of hybrid cloud, AI-assisted software engineering, and developer productivity tools. His current research focuses on AI for code, with recent work on code understanding, code summarization, and code question answering, successfully applying natural language processing and large language models to these advanced areas. His research has been published in top tier international conferences across software engineering, NLP, and artificial intelligence. Beyond his technical contributions, he is deeply passionate about mentorship and actively guides students through the IBM AIHN programs, helping them explore cutting edge research in AI and software engineering. So, yes, that's it for the introduction. Over to you, Shrikant sir.
Yeah, thanks, Sejame, for the introduction. Glad to meet you all. Good evening. So today I'm planning to give a guest lecture on summarization. So this is what I plan to cover. We'll look into the motivation of this whole research. We'll go into the details of text summarization. We'll see some of the interesting properties of code and its representation. And then we'll slightly go into the literature of code summarization. And along the way, we'll look into some problem statement that I've been able to work at my end and along with collaboration with IIT Bombay in the related space of summarization and its quality measurement. And finally, we'll conclude by looking into forward-looking research opportunities. Okay, so quite informally, if you have to just think about summarization, right, you can think of it like trying to extract some key information. For example, if you have a fruit, maybe you might want to keep the juice and discard the pulp, right? But it can be a subjective opinion, so that's why it's also an interesting problem. If you have to have like a slightly more formal definition, you can think of summarization as a process of compressing a large amount of information into a shorter, concise form while still maintaining the core meaning and essential details. Okay, so there's a lot of key terms that are packed here. We'll see the significance of them as we go through this lecture. And it's just not for text or any specific modality, right? It's applicable in their daily life. For example, even now, right, I'm planning to give a short version of the research in summarization. So you can think of this like a practical application that every one of us do on a daily basis. Why are we even interested in all this, right? So this primarily because of the data explosion. So what was just a small amount, 64 zettabytes of data in 2020 has grown to 3x by this year 2025 and is further expected to grow to 4,000. If you're wondering how much is one zettabyte, okay, so you can just have a look at this. You can just try to count the number of zeros from your end. Okay, but fun apart, so we know the data is growing and then most of the data is in unstructured form. So it's a better way to store the data. There's a better need to consume the data. So that's why this whole research is very active and interesting. Okay, like I said, the modality of data is also widespread. So there's a lot of focus modality specific. For example, there's like a lot of active research happening in how do you condense large articles, books, etc., primarily under text summarization. There's equally good amount of work that's happening on audio input. For example, how do you effectively summarize meeting discussions? Similarly, you guys must be aware of the trailers, trying to how do you come up with good highlights of the stream videos. There's also a active, equally good amount of research happening in the code space also. Again, in industry, there's a lot of code is written, and there's an easy way to understand them. Try to have a good definition of some of the APIs, functions, etc. So in this talk today will focus more on text and code modality. Okay, so here is a quick example of a summarization system that try to compress this what you have like a slightly longer text document into this smaller version of it. So I think you might observe two key things. One, the number of words that is used to express this content has been reduced. To be precise, it had 84 words. It is now reduced to 24. And I'm just also highlighted certain words, and you will see a representation of it in the right hand side. You can consider this as a summary. And another thing that you will notice is it is spread across the whole paragraph. So what a good summarization system should do is it should have a good coverage. It should look into all key aspects, and it should be able to look for all the aspects in all the different places of the document. Okay. So with that definition, let's look into how we can perceive this whole summarization system. There are multiple like lens to look at it. So you can think of this whole summarization from the point of view of the input. So there's a lot of active work that try to demonstrate effectiveness with a single document text summarization system. But increasing the corpus comes up with its own challenges and interestingness. So there's a lot of right interesting work that try to handle multiple documents and try to come up with good effective summary. You can also see it from the point of view of intent or usage. So predominantly the lot of work is focused on just summarizing the given document, but there's also a significant research that has gone in that also focused on user query based. So for example, as a user, I might have a specific intent that I might express for which there will be a relevant content or the context. From there, you need to first retrieve the relevant context, and from there you need to either use the extractive, abstractive, the different approach, and then summarize. That leads to the approach. So from the point of view of how you want to summarize, so you can either try to look for interesting sentences, paragraphs, and just extract them, or you can try to understand the whole topic and concept that is written in the document and then try to generate them, right? So the good thing is you can sort of have a different way of expressing it, maybe lesser meaningful words to express the same content with abstractive form, but it's slightly more challenging than extractive summarization. And there's this hybrid task of right combining these two approaches. There's also a lot of work that focused on right multilingual and crosslingual. Monolingual is quite common. So you have a input text. It can be in one language, and you try to create a summary of it in the same language. A multilingual summarization research focuses on input being it in multiple languages. It can be English, it can be in other languages, it can be a combination of code and English document in different languages again, and then you try to have like a target language to convert to. There's also this cross lingua, wherein your source document and the target summary, their language preference are completely different. For example, trying to take a English document and then trying to produce a Hindi summary, which is very much a need, right? It's also an active research that's happening, and we have some research happening with IIT Bombay on this problem statement too. Besides this, there's a lot of research that focus on creating a general purpose summarization, but also a very domain-focused summarization system, especially in medical fields, legal work and all. The choice of words matters a lot. So you need those domain exposure to make sure those domain folks they accept the produced output. Okay. Finally, the output type also, there are different forms that have been explored. One is indicative, so wherein you don't try to give the summary of the content, but just try to maybe give information about the topic so that the user can decide whether there's a merit in reading it. And the usual informative one where it tries to cover all the important information in some condensed form. So this is broadly, right? If you look into the whole text summarization research, you'll be able to right, position the papers in one of these buckets, one of these buckets. So let's look into how a typical text summarization system works. So you either the input is usually a document or a multiple documents, and there can be an optional user query to drive the whole summarization. And based on this, there can be some pre-processing steps that can happen. For example, typically people do write converting the document into some lower text, removing some unwanted content. For example, many of the times there might be some tags that are there, like HTML tags, etc., that you would want to remove. Then folks might want to try to uh, create an intermediate representation of it, be it some ngram based or graph forms, and then they apply the approach to create summary, and then they apply some post processing to make it consumable or more suited for the target user or persona. So this is usually what happens. And if you have to little bit discuss like how does it happen in the extractive summarization system, then what you can think of is like after this whole pre-processing, usually what happens is you have some kind of scoring mechanism to score some sentences. The sentences can itself be scored, or sometimes if it's a graph form, then you try to look for the importance of it. And then you try to pick those sentences that you believe will make a meaningful summary. And in the post-processing, sometimes you might want to reorder so that the coherence is maintained. So this is what typically happens. In the abstractive form, instead of trying to pick sentences, what you try to do is you generate them. And usually what happens is you try to create an intermediate representation of it in any forms. And then you sort of try to have some heuristics or some machine learning based approaches to kind of start generating those sentences. Okay. The final one, like I said, is query focused one. So in this particular example, what you say is there's a document about ISRO. So it covers three key topics. It discusses about the launch details, its mission goal, and then some of the agencies that helped, right, or supported this whole mission. There are these three concepts. So as a user, if I have a query about what is the goal, there's no point in me trying to give condensed information of the whole document. The first task is to identify the span of the text that is relevant to the query, and then try to explain right, the query. So in this case, you can see that it was able to identify the highlighted yellow text, and in this case it's abstractive summary, so it tries to explain it in its own newly generated words. So this is how typically the flow goes for query focused summarization. Let's look into a bit on the evolution. Okay, so this whole summarization, if you like follow the literature, you will see that it has been happening since 1950s. Okay, so until 1990s and early 2000s, the bulk of the focus has been mostly around using some handcrafted features and statistical methods to come up with a strategy to summarize. Later on, when neural networks picked, there was this whole research around supervised way of learning to summarize. After the advent of pre-trained language models, especially BERT, there was a lot of focus on how to better leverage self-supervision and fine-tuning to do better summarization. And now recently with LLMs, people are trying to exploit some of the emergence behavior to use summarization systems in the context they want. So if we have to just touch upon some selective works, again, there are a lot of significant work that happened. I'm just highlighting few of them for the reference here. So there was, like I said, there were a lot of works on heuristics to summarize. Maybe it will sound strange now, but some of the popular works looked into the position of certain words. They also looked for certain keywords and then which section they belong to. There are a lot of heuristics that were involved. Later on, there was this concept that came out, right, called as maximal marginal relevance, wherein they try to not only just pick sentences that try to have more similarity to the query, but also they try to increase the informativeness in the whole output. So they wanted diversity. So they introduced this whole score measure. And what it says is like, how can I give relevant documents, but at the same time give information or like produce those sentences that are diverse from the already produced sentences. Okay, so that's the whole concept. So then people started to take it as an optimization problem. They wanted to increase the coverage of informative sentences, but at the same time, right, they wanted to make sure that there is less redundancy with the previous selected sentences or generated sentences. Then there is a lot of work which came from graph-based approaches like LexRank, etc., wherein it tried to take each sentences as a node and try to look for similarity with other sentences, and then they try to look for key sentences to pick based on the node centrality. Okay, so as you can see, right, there is a lot of heavy duty work on handcrafting these features, and it's all superficial, right? There was no rich semantic understanding of the content to do the summarization. So those were some drawbacks, and that sort of slightly got fulfilled. That gap was addressed with this whole deep learning based methods, especially sequence with attention mechanism. So it was able to use a lot of supervised data. So for example, during this era, a lot of effort went into collecting those pairs of documents and summaries and using them to teach model to slightly align with human intent, and they were able to produce better summaries. But the challenge was with the whole architecture itself. So the long context retention was a challenge. So that was one drawback. That and another one was like there's a heavy reliance on collecting this huge corpus of paired data to do any meaningful training. That got slightly elevated with the advent of pre-trained language model, because as you know by now, right? So this whole language model runs with the concept of self-supervision. So you just have your knowledge data, and then you introduce some tasks that are like that can be done without any external annotation. For example, the task of mass language modeling or next sentence prediction, etc. So I'm just calling out two significant work that were heavily used. So this BERT-SUM-X, so this is an extension of BERT, and there were two interesting things that they did. One is this was one of the first paper that showed how to combine the general text document with code data. And another is they also introduced this thing of two-stage fine-tuning. Okay. So they use first limited amount of extractive data and then abstractive data. And then they also had introduced two kinds of optimizers, sorry, for encoder and decoder. Okay, so that's one thing that they introduced, and that gave them good performance compared to a lot of very heavily supervised models. Then this is Pegasus. Um, like I said, if you have your own knowledge document, then you can try to come up with some task-specific pre-training objectives. This is one thing that they did. As you know, earlier the next sentence prediction or this masking was quite common. So here, what they tried to do was to introduce such a thing here. So they introduced two pre-training objectives. One is again, the encoder is supposed to learn or detect the mask tokens. And then the decoder is supposed to fill the gap. So you can see there are three sentences here. So the decoder is supposed to predict the masked sentence. That is here in this case, it is pure white. Okay. So this kind of good, interesting objectives to learn from the knowledge document, was very beneficial, and they were able to help a lot in the whole summarization system. Okay. But then, like I said, even though the reliance on supervised data is reduced, there is still a decent amount of supervised data to be used for further task-specific fine-tuning. And and the generalization of the system was slightly needed to be improved. Okay, those were some concerns, but definitely they were able to better handle domains. And this was a time where you can see a good boost in the performance of abstractive summarization. Okay. Now, in the era of large language models, what you see is you have these very large language models which are meant for general purpose, but without a lot of fine tuning, you are able to adapt to new domains with different prompting strategies like few shot training, or if they are not able to follow some instruction, then you can do instruction fine tuning, or you can use some adapters to further align the model, etc. Okay, and on top of that, very recently there is a lot of focus on using agents, basically a combination of multiple LLMs or tools to get the whole summary done. Okay, so we'll just go into the details of them a bit in detail now. So like I said, with the advent of LLMs, these are the prominent ways of modeling. One is prompting based. So typically when you have the model and you are asking like, can you summarize this document? You can consider them as a zero shot attempt. So you're just giving the instruction and then you are expecting an answer. But if you have some desires, for example, if you want the output in some certain style, or if you wanted to follow some formats, or if you wanted to maybe be rich in some particular domain, you can give some in-context examples. So, you can try to have this pair of input outputs as examples. In this case, I'm just showing a three-shot prompt example, and then you can have your question. And what people have observed is many of the very large language models, they are able to do well because they are exposed to so many domains. They can easily learn from the in-context example and adapt. Again, even then there are those certain scenarios when it's not doing good. So then people started to explore more on the prompt engineering research itself. And there have been a lot of good research outcomes that have come in the form of chain of thought prompting, etc. And one such thing that came was this whole notion of prompt chaining, wherein you take a complex task, try to break it into more simpler tasks, and have individual prompt supporting those broken down tasks. Okay, as an example, here is one work that try to do this kind of breakdown for summarization. So in this case, they had a document, and what they did was they were able to break down this whole task into three steps. First, they asked the model to come up with the initial draft of the document, a summary. Then they try to have the same model to critique it, to so that they know what are some of the gaps that needs to be filled with the produced summary. And then they take the original document, the generated summary, the critique input, and then they further prompt the model to refine them. But here the onus is on the user to try to break down the complex task and then do it. You can also try to ask the model to think of possible ways to break down the steps and then do it. So that research is also popular. Or you can also try to ask the model to follow some of the steps that you believe are good to address this task. But then instead of doing it through three LLM calls, you can actually have this whole thing as different steps. Let the model internally reason down and then try to produce the final output based on this intermediate steps that it needs to follow to produce it. So this is like the chain of thought kind of prompting is majorly done through this, where they define the steps or they simply say like things step by step. Then it tries to take its own time, reason out and then do it. But it's slightly inference cost heavy. um, Again, the research kept few more kept on exploring few more ways of intelligent prompting that might help in whole breaking down this challenge of meaningful summarization. So this is one such work. So here, what the authors tried to do was they identified from the literature that for any good news article summary, there are four key concepts that are important. First, you should be aware of the entities. You should have a good understanding of the event. You should have a good understanding of the date, and then a good summary should also capture the result of that event. So, if this is how a good summary should look or like should definitely contain, they make sure that they probe the model to focus and try to get these answers as intermediate steps and then use this answer to produce the output summary. So this is where, even if you have powerful LLMs, having a good understanding of the domain having a good background on the kind of documents that you have and the expectation of the users will help, because when you have them you can try to probe the model in different ways so that you get the desired focused summary. So these are some good interesting work that can be beneficial. Very recently there's this whole interest in using multiple LLMs to produce the output. So if you have like if like in the past it will be the job of only one LLM to do the whole summarization, but very recently they devised a strategy wherein they believe that this if you have the same model to critique, it might not be that unbiased. So they started to involve multiple LLMs, and also there are some critical information that you might not get with the system at hand. So they might use a very task specific LLM to retrieve certain information. For example, having a understanding of a particular domain, or trying to look up some live events, etc., to follow the question of the user and then produce output. So these involve having access to external tools, involving multiple agents. So this is where majority of the research is going on. So if you guys are going to pick on summarization as your research topic, you should definitely follow this whole usage of multi-agents and agentic framework, and how people have been able to chain this whole possible options of LLMs and tools to get the desired summary. Okay, and there are those scenarios where the model has all the sufficient knowledge, but it's not able to follow some instructions, or there's a desired kind of output that they want. So especially in commercial sites and all, you might want the information to be available in certain forms, etc. So in those cases, if you know like there's going to be a repeated request and you want to be certain of your output to be of that desired format, then you can also do this instruction fine tuning. Okay, So here is an example. It's an industry study from Amazon, wherein because of some reasons in their internal way of managing information, the item name has a lot of information apart from the item name itself, like the characteristics, and then the size, etc. So then it becomes a whole challenge when the end users are trying to have some chat experience and trying to search about a particular item. Then they are not able to get a good match because what they perceive as a product and then how the Amazon system was saving them were different. So there was this interesting challenge of how do you come up with take these long names and try to have good titles, and then based on the context also better produce enough sub information of the long title that will be meaningful for the end users. So they try to instruction fine tune this whole information. So this is one more interesting work. And this is a practical use case. So what happens is with large language models, a lot of enterprises are not able to immediately use them because of the GPU need. Okay, so it costs a lot of money and resource to host LLMs. So that's why many of the enterprises are looking for tiny LLMs. But then you want a good way to have a reliable tiny LLM that can have at least performance very similar to the large ones for this narrow domain. But at the same time, right, make sure the sizes is reasonable and they can afford it. So this whole knowledge distillation is widely used in such scenarios for those narrow tasks. Okay, so the basic concept is you have a very large model and you try to probe it, and then you try to create good fine-tuning data from it, and then you train a very small model. So this whole big one can be thought of a teacher model, and then you try to take a small student model, and then distill the knowledge, and then the small LLM tries to behave like a large LLM for that narrow use case. Okay, so this is another popular work that has a lot of industry relevance that are happening right now. So if you go for internship, you will see many internship problems around this topic. So over the years, there have been a lot of data sets. So if you're getting started in this whole research, you will come across these data set. Again, the data sets are available in multiple domains. Folks are trying to actively come up with new data sets because any data set that you produce now, they become easily available for new training, and they quickly become irrelevant because the LLMs are getting stronger and stronger. So how to effectively come up with complex data set is also a good research problem to focus on. Now that we looked into approaches and then data sets, the next thing is how do you measure? Like I said at the beginning of my talk, this whole topic is slightly subjective, right? What one person perceives as a good summary may not be universal. The other person might feel not so good about it. Okay. But then there is a need to measure so that you at least have a baseline of somewhat acceptable summary. So there are these three key aspects that research look into while trying to perceive the quality of the summary. Those are correctness, completeness, and conciseness. Correctness to a large extent is factual, so there can be some heuristic, deterministic way to do it. But then completeness and conciseness is more subjective. Okay, so because you don't want every topic to be there in your output, so how do you rank the importance of topic, right? So that you can say I have all important information, right? And how do you say if information that you have is right to the point? So this is difficult. So yeah, this is still an ongoing research problem. So correctness looks into if all the details that have been generated in the summary are accurate. Completeness looks into are all information, important information documented in the summary. And conciseness looks into is only the important information captured, right? Or does the summary has some not so relevant information or less important information. There are other aspects like fluency and etc. But these are the three key aspects that we see as important measures of summary quality. There have been some metrics that have been proposed that helps to measure. Many of them are reference based. One such example is RUGE. So it tries to measure the overlap between the reference summary and the generated text, either for some n-grams or some longer subsequences. The focus is mostly on the recall. Okay, so here's one such example. So you have a reference ground truth that says like Chandrayaan-3 successfully landed on the moon. And if your generated sentences Chandrayaan-3 landed on the moon, you see a heavy overlap. There is definitely right successfully keyword that is missing, but then most of the other words that are there in the summary is also there in the generated text. So you can think of them as like it has a good high right root score, and it can be an acceptable sentence. But as you can see, right, Rouge is mostly based on word overlap. So if you have a paraphrase, then right, Rouge is not a reliable metric. And with abstractive summary, that's a big challenge, right? And also you want to have a good understanding of some connections, long connections within a paragraph or the final output. So in those cases, word overlapping metrics may not be helpful. Okay. So the other popular way of measuring it is using BERT embeddings. So they try to look for the semantic similarity using cosine distance between the generated summary and reference summary embeddings. Okay. So this is also widely used. So if you have ground truth, people can look for Rouge, but it has its own challenges. Otherwise, people can also use embedding based similarity measures like BERT. Apart from that, there are some interesting ways of measuring. They are not as reliable and as commonly used, but then in certain use cases, they have been found beneficial. One such thing is this QA eval. So if you have a generated summary and if it's truthful to the context, then if you create some question around it, you should find an answer in the right in the reference document, right? So people try to lean on this concept, come up with this QA eval metric. Besides this, in some narrow domain, there has also been a work on trying to train a classifier that tries to classify the generated sentences if they are factual or not. Again, not widely popular, but in very, very narrow use cases, these have been applied. Now, a very common, increasingly reliable way of measuring the quality is using an LLM itself to judge. Like I said, a very common approach is not to use the LLM that is used for generation as judge, but use something else. But ensuring that the LLM as a judge is right has a very good knowledge of the domain and generally is bigger in size so that it has more reasoning capability. Okay, so this is again widely used now to judge, and the good thing is like you can increase the number of dimensions, right, that you want to measure. Like you can have very focused prompt to look into the summary correctness or the completeness part or any other dimension like fluency or the overall score, etc. So these are quite popular ways of measuring it. Now we look into the second part of the talk, which is on the code summarization. Like I said, there's a lot of work that happened on text summarization. Many of the work that have been done there have been influential in the code summarization research. Very formally, code summarization you can think of as a task that tries to understand the code and can generate some description from the code itself. Okay, so here's an example. It's a Java code that tries to write index a name, and it has like few code statements here, and you can think of as code summarization task to create this kind of quick documentation of the Java method. Okay, and why is code summarization relevant and right actively worked on? In industry, there's a lot of surveys that have been taken at different points of time. Consistently, right, the amount of time the developers have spent on understanding the code has been one of the major challenges reported. Okay, and it often happens that the developers will have to work or maintain somebody else's written code, then it becomes even more challenging. And many other times, the developers themselves are new to a programming language, so without those comments, they'll find it more challenging. And there's also a bad habit of folks not trying to write active comments as the code. Even though we stress a lot, there are still those scenarios because of some time crunch and basically with the nature of the developers, they tend to skip it. And sometimes it can be oversight. For example, folks might try to change the logic of some code, but they don't try to update the code change. So that can have even more bad effect. So these are some reasons why there's a need for automated code comment generation systems. Okay, but how do people deal with it? So one thing is they try to make sure they try to have more meaningful names, be it right variable names or function names, etc., so that it makes sense. But still, it doesn't solve the need for a good right documentation. So that's why there is a need to automatically generate comments and a need to prompt developers to write comments when they don't. Okay, so before we go into some key works that happened in code summarization, I just want to take a couple of minutes to introduce to some special aspects of the code. Okay, so code you can write, think of it as like a sequence of some tokens, and many of the large language models, they have considered code as text only in their processing, but they also have some good properties that can be beneficial. They have not been properly utilized. There are some works that have used them. For example, from code you can also extract something called as abstract syntax tree. So abstract syntax tree, what it tries to do is it tries to give you a good information about the structure of the code. So wherein it ignores some of the parentheses and all, and then tries to give a good information, a tree information of the structure. It also gives you information about the execution flow. Okay, so you can think of the different code blocks as nodes, and then the various flow that can happen has some edges. Okay, so most of the time the conditional statements determine the path. Okay, so this kind of graph information is right something unique and right can be very beneficial. It also has other outputs like data flow graph. It gives a good information about the usage of certain variables in the program. So like I said, you can think of code as just some continuous series of tokens, or you can also see that from the lens of tree or graph, right, that tries to capture the different syntactic and semantic properties. And there have been good amount of work that tries to combine them also and see if they can benefit. You'll see a couple of papers that I'll go through that have been able to leverage them. But then, to be honest, like treating it as a series of token itself have been helpful. But we know, there's also an active research that tries to combine the rich features that you can extract from code in combination to a series of tokens and then, have a better modeling experience. So with that, we'll just look into some code summarization techniques. So almost all the work that, all the different key works that you have seen that have been employed in the text summarization, you will see a reusage or a usage of it on the code side also. So, like I said, the tame burst or handcrafted feature-based summary, they have been also used. Whatever was studied there by looking into the position or the importance of tokens in the document across document, they have been also used in the code setting where each program can be considered as a document. Um, but then besides that, there are some interesting work that happened on the code side by trying to look for some similar code and then trying to take their descriptions, etc. And again, on the ML side, whatever techniques that came and were applied on the text side, they were borrowed and tried to reapply on the code side with some small tweaks. So we'll see just few of them. So like I said, the popular approaches of using TF, IDF and all, or topic modeling, they have been also used considering each code file as a document and try to look for important code statements, and then for them they try to extract some key tokens from them and then use it for summarizing the whole method or class file, etc. Um, this particular technique, the template-based summarization, was also widely used because there is a kind of expectation on code summary, especially if you're trying to summarize at a method level or a class level. So you already have a good idea of what is expected. So people tend to create template. For example, if you look into many of the traditional code, like for an example, Java method, you will see documentation containing input output, brief summary, and return. So you can think of like these are some key information that anybody would want. So people try to create those templates, the following method, and then they'll have a placeholder. And there have been a lot of works trying to look for those, trying to fill those placeholders by traversing the code. Okay. Surprisingly, this was very widely accepted, and they were used a lot. But obviously, you need to have an intelligent way of picking the templates based on the code characteristics. That's why recently it's not that prevalent. So there were some works that tried to also look into some similar code and then try to take its summary and then reuse it. For example, code clone detection is also an active work, wherein for a given code they try to look for similar functionality code in the same language or different language from online repositories or internal repositories, and then if they have some comments, then they sort of try to reuse them. So this was some popular work that happened. Later on, like I said, with the when sequence to sequence model was introduced, then there was this work that tried to use it on the code side also. And naturally, when transformers were introduced in couple of years, transformers were also applied on the code setting. Like I said, whenever they introduce, they try to slightly adapt considering the code characteristics. For example, when this work was introduced, they tried to introduce two small tweaks compared to the original transformer paper. One is the usage of relative positional encoding. Instead of trying to have like a absolute positional encoding, what they preferred was based on the usage of the variables, the position can be different. So instead of having a hard positional encoding, they got influenced by Shaw et al. Work and then used relative positional encoding. Second thing is they wanted to retain some of the user-defined variables that may not be available in the vocabulary. So they sort of used this copy attention. So at the time of generation, they decide either to generate or reuse the input token itself. So with copy attention, they were able to retain many of the words. Okay. So these are some small tweaks, but largely the architecture is the same, and they were able to demonstrate on code. And I think this was one of the first work that tried to use a combination of natural document and code document to do well on code task. When BERT came, like soon there was this work also called CodeBird that came. Again, they had a small tweak. So they introduced a different pre-training objective called replace token detection. So randomly they try to replace some token, and the discriminator is supposed to identify whether the token is original or replaced. That helped them better code understanding. Okay, so again, with LLMs, whatever we learned, whatever we saw with few shot learning, those are also regularly used here. So just like you have some question and answer pair of document and summary, here people try to research on what are the meaningful code snippet and summary pairs that can be extracted. It should have good diversity and it should have good relevance for the input code snippet that needs to be summarized. So many of the work were focused on how do you retrieve good in context sample pairs that can be used for the generation. Yeah, so these are some data sets. Code SearchNet is quite popular. I think in the past I mentioned about Codex Clue from Microsoft. That had samples on code to code, code to text, text to code, text to text, like text to code task. But again, if you currently look at them, many of the frontier models are absolutely beating everything in those old benchmark sets. So at least in industry, we are working on coming up with more enterprise grade code snippets that we actually encode there, and we see that the performance is not that good. So you will see many of the companies may not be able to publish the data outside because these are all some proprietary code. Um, uh, but the numbers are not as great as what you see with this public data set. So there is still active research that is happening, and there's a need for more research to bridge the gap. But definitely, there's a lot of improvement in the general quality of summary generation from what we used to encounter like 2-3 years ago. Now, what we'll do is I'll just also discuss few papers that I was able to work with IIT Bombay and my team that has something to do with summarization or measuring it. Okay. I just hope that these set of papers serve as an inspiration to further your research in any of these areas. So one such work is this work called Agentic Multimodal LLMs for software comprehension. So this work was done with Ashita. So she was also a student from IIT Bombay, but now working with me at IBM Research. So this work tried to look into some missing gaps with application level explanation. So you can think of it like how do you explain a repository. So here is a quick reference. In public, if you just look up, there is a popular repository called DayTrader. It's a repository open sourced by IBM that is to do with online trading system. Okay, so it has some code written in JSF servlets that tries to mimic an online trading system. and it has different capabilities exposed. Okay, so when we try to use Copilot or Claude on it, this is the kind of output that we got. And basically, right, this particular trading system had a few more capabilities. So I'll just maybe briefly tell you what they are. But for our observations were, the summaries that were generated were more syntax centric. So for example, as an end user, when we are asking for a summary, we want it slightly in the abstracted form, wherein we don't want to focus a lot on what is that file, what is that thing, right? What is the syntax, but more focused on what does this application do, right? What are the key capabilities it exposes? Not saying like these are the X files that are there, and right, trying to describe the information from the names of the files alone. Okay. Second thing is there's a natural way of consuming some summary. For example, if I'm if I'm asking about an application, the, it is best for me to consume from the point of view of its usage. For example, if I take the same trading application, so this application supports onboarding a user and letting a user to be authenticated, to be logged in, and then helps to look up his portfolio and then decide what to buy or sell, right, and then also look into the market information, etc. So this is like a natural workflow for me to consume this information. But if a summary that does not understand the natural workflow and gives me random information, like for example, when I start reading the summary, if the initial paragraph discusses about performance, and then suddenly it discusses about trading, and then suddenly it discusses about how users can be authenticated, it lacks that coherence, right? Or I would say a natural way of using this application, which might put off the end user. So this we felt as unnatural sequencing, and right, it needs fixing. And apart from that, the choice of words also matters. You cannot have like standard set of words to describe any repository. If you understand that this is a banking application, then a choice of word, if it related to banking, might help the user consume it better and faster. So these were some drawbacks that we saw. Okay. So again, this is still a summarization problem, but summarization problem at a repository level, wherein you are not only focused on summarizing individual files, but you have to have an understanding of cross files, and then how they all come together, right, to support the different features this application exposes. So here is one example of, right, if we were able to get away with all the drawbacks that I mentioned, how it will look. So you can think of this as a ground truth summary. So the order is there. So it discusses about user login, portfolio lookup, portfolio view, code lookup, and then doing the whole trading. Okay. And then as you read is, you can see right, there's a the sentence are coherent, and then they are still a very succinct form of the whole repository information. But what does it take to have such a system? One thing is, like, you cannot have just one LLM call to make this happen, and you cannot, how much ever you try, or we did try to come up with a very very detailed prompt and give all the information to come up with a summary, but still it was not enough. We did all this prompt engineering exercise. Then what we realized is, like, we will need very specialized LLMs and tools to do this repository level explanation. So what we did was, we had to use a combination of program analysis, natural language processing, and some reasoning on top to this whole summarization. So what we ended up was like having a very specialized LLM agents, and then breaking this complex task into small tasks and having a very specific agent responsible for it. So it made our life easy to measure the effectiveness of each agent, and how to put together them to get the desired output. Okay, we'll just see a quick flow of how we did it. So what we did was, like, we took the whole repository content. So it had a combination of the program files, the .java files, and then text files like readme.md, etc. Readme.md was also meaningful because it had some information about the domain, and also some capability information. Then what we did was, to understand the capability, we wanted to understand what are the ways in which we can interact with this application. So those are usually exposed through APIs. So the first task was, we needed a tool that can try to identify the different API endpoints. So that's what we did. So we tried to break down this whole problem, and the first task was employ a tool, a program analysis tool, that can extract these different API endpoints. And since it involves program analysis, you might not be sure with static program analysis to identify all the possible entry points. So we sort of had a measure, like, after doing this program analysis, are we confident that we have enough information to identify the capabilities exposed or not? So with that information, based on, right, whether you have or if you don't have, we give all the program files as an input to the next agent. So the next agent, what it tries to do is, it tries to take this information, but also focuses on the non-Java file information, like the readmes, and then tries to see if those readmes have some meaningful information about the domain and the capabilities, etc. So this agent involves right, how to parse the text document and try to extract those sections, and try to link sentences that are related to common capabilities, etc. And with the earlier information, the next agent was trying to predict the number of capabilities. For example, with the entry points and the readme for this day trader application, it tried to determine there can be like this 5 different capabilities of login, stock trading, portfolio management, session management, stock lookup, etc. Then the next step was to determine if right, to another LLM, right, whether the workflow is correct, or how to arrange this whole capabilities from a workflow point of view. So it tries to, you can see, right, here we are trying to order them. So we assume this LLM is more has a more understanding of the different domains, and then based on its domain knowledge, it tries to order the different capabilities that has been identified. With that, this whole information is given to a summarizer agent, wherein it tries to produce a succinct summary that can be later on used by the developers. So you can think, right? So because we have the flexibility to use multiple LLMs, and then the LLMs generally are quite powerful to reason, we were able to handle this kind of complex problem of summarizing large repositories which can have, right, tens to hundreds to thousands of files, and also having different content, like some text content, some right, like code files, etc. So this is one work, right, this is the work that got accepted. And we also studied with some popular applications, public applications. We were able to reliably do well. Just in one of the applications, this whole agentic workflow, it missed to identify one capability, but otherwise mostly we were able to identify all key capabilities, and we were able to also match with the human, right, annotated workflow. This second work, this was very recently accepted. While working on this whole right code summary, be it in the context of single file summary or repository summary, one challenge that we often faced was how do you detect hallucinations? How do you mitigate them? So this work was one step towards it. So Kishan from IIT Bombay worked with us as summer intern, and right, we were able to address them. So hallucination, the general definition from psychology is that it's a kind of a perception felt by an individual without any external stimulus. But in the context of NLP, you can think of them as some information that might look correct, but is not relevant to the reference, right? And or something that's unfaithful to the reference that you had. And broadly, the research identifies two kinds of hallucinations: intrinsic and extrinsic. Intrinsic hallucination, you can think of those wherein the output produced contradicts to the context. So as an example here, if you have a document that says like Marie Curie discovered radium in 1898 at the University of Paris and blah blah blah, if your summary that you generated has the sentence called as Marie Curie invented radium in 1898, it clearly contradicts with the document because discovery is not the same as invention, all right? Because discovery is something that is available, but you just right, nobody else realized it. But invention is something that you created new. Okay, so this differently, right? It's not the same thing, but you have. But for this conversation, the important thing is there is an input document, and there's a way for you to right verify them, and you know that there's a contradiction. So these are somewhat right. Ideally, they should not happen, but at least if they happen, there is a way to right identify them. Extrinsic hallucination are more difficult to identify because your reference text might not even have a reference to the generated sentence that you want to verify. For example, if you take consider the same document, and if your generation somehow says like Mary Curie was born in Warsaw, Poland, from the reference input document, you don't have a reliable way to say whether it is true or not. These are generally called extrinsic hallucinations, and they are even more difficult, right? Difficult even for the humans, and very definitely more difficult for some of the automated measures that we have to detect. Now, in the context of code summarization, this challenge is definitely there because the large language models are generally very good in producing very convincing text. Sometimes becomes very difficult to identify them. Okay, so it will be very convincing, but if you start to really inspect, you will find that there are some sentences that are not true to the input code. And one of the things that we largely saw was these models tend to be misled by some of the right method names and the return types, etc. Okay, so by some of the identifiers. As an example here, you see the input, the left hand side code. The code returns int, and then the method name is get job ID. It takes a job name string as an input, but it just returns -1. Okay, but because the method says get job ID, there are some models that gets misled by it and tries to hallucinate, saying that it's trying to fetch a job ID with job name as an identifier from the database, etc. Definitely, that's not what this code does. And is right also another example wherein because it says run job, but ideally a developer should not have named it as run job. But anyways, if they did it and the logic does not right stay true it, the model can be misled by such syntax, and then it can assume that it's running a job with the right identified job ID. So these are some actual instances, and these are quite relevant. Okay, it does happen, and there's a lot of challenge in consuming the LLM's output, right, because of these kind of scenarios. So to formally study this, what we did was we took this code as clue dataset. Like I said, they also have a task towards code to text. basically code summarization task. And the data set is available for 6 different languages, but to make our life easier, we started with Java. And then we thought like we'll try to study on that Java dataset. One thing we intentionally tried to do was we did not try to artificially create any samples. So we did not try to perturb the samples and then try to force a model to create hallucinated summaries and then try to detect them. What we did was we took some of the frontier code models like IBM Granite, Llama, Code Llama, Mistral, mostly open source models. We didn't want to spend a lot of money on frontier models. So we took this easily available models and then created summaries. And even there we had different choices. We created summaries at a simple level, trying to get a general business purpose, or give a more detailed view of the code. So these were 2 levels of summaries that we produced. And then we started to annotate manually. We started to see like what are the kinds of hallucinations that we observed in the generated output. And we were able to look into some factors, and this is the kind of taxonomy that we came up with. So we found that a lot of time there was a identified name bias that led to the hallucinations. Like we just discussed, right, with those examples on the function names, variables, or library names, they misled it. There was also a lot of time where some of the methods had some external library reference, and because the model does not have more context beyond the input code, it started to hallucinate because it didn't have enough knowledge about that external library call. It started to just make up for it. Okay. And sometimes it did not have a good understanding of some of the recent annotations also, like with Java, with the different frameworks and versions. JDK versions, you will see like some new syntax forms that are introduced. If the model is not trained with those latest knowledge data, it will not have enough information, so it will start hallucinating. So we saw instances of them also. Beyond that, there were some code which was very lengthy, and sometimes the logic itself was very tough, even for us to understand, like with so many loops. In those cases also, we saw the model was hallucinating. And there were some instances of methods wherein the comments were not up to date or contradicting. And the model were instead of focusing the code, they focused on the comments, and it introduced those hallucinations. These were our observations. And then this is the kind of distribution that we saw, mostly to do with code complexity, but then like a lot of external library calls, and then the name bias also uh, forced a lot of hallucinations in the output. So then we thought of if we before mitigating, we wanted to see if we can reliably try to identify them. So we came up with this simple framework we called as entity tracing framework. So it had 2 key stages. One is entity verification, and another is intent verification. So entities you can think of like all the key identifiers from the code. It can be your function names, it can be your variable names, etc. So and we were able to extract them from using language specific parsers. Like you can use tree setter, you can use Java lang, etc. Similarly, on the summary side, we try to look to extract entities. Tools like Spacey, NLTK, they were not good in identifying such code entities in the code summary. We found them to be not reliable, so we were forced to use LLM for this task. So we used LLM to do this named entity recognition task, and we were able to extract them. Then because this involves LLM, we knew that in this stage itself, the LLMs might hallucinate. There can be chances wherein even if you probe the model to extract entities from the given code summary, it might hallucinate because it's still a generation task for LLM. It can fabricate some entities. So we try to actively filter those entities. As in this example, we try to extract an entity or generate an entity called end time, but there's no mention of it in the code summary. This we call as fabricated entity in identifying the named entity, NER, in doing the NER task, and we drop them. Then whatever entities are left, that we try to see if there's a reference of it in the source code. If it is available, then we try to look for its intent. But if it's not available, then those we consider as extrinsic hallucination. That means it introduces content outside the source code context. So we don't even try to map them or try to look for the intent. So we drop them. So we are finally left with those entities that are extracted from the code summary and for which we have a reference in the source code. Now the task is whether it is used in the same intent as what is used in the code. For example, if you find an entry called get job ID, in the code, it tries to accept job name as an input, right? And it returns an integer type. This is a description of job ID, get job ID entity. So what we then try to do is try to look for those text and then try to see in the context of that code statement, is it doing the same or not? Basically, we try to verify the intent of the identified entity, whether it is correct or not. So this is how we try to use combination of LLMs to detect hallucinations. It involved a lot of manual work to identify hallucinated summaries, identify the span of text, identify all the entities, and then trying to say like this entity, it appears in this code statement and this is the intent of it. So we captured all this final level information, but this information is now available for the research community to work on. Okay. So on similar lines, because we were so much focused on the quality, we tried to further see, look into all the metrics, and we were trying to see whether there's one easy way or one common metric that we can reliably use to measure the quality or not. In, like I said, in text also, there's a lot of metric in many of them are also used in the code summary context. But apart from that, in code summary, there were few metrics that were introduced that are not there in the text domain. There are metrics like side that tries to see how aligned the generated code summary is with the code. Okay. So there are a few metrics that are very focused on the code properties that are available, but still none of them are reliable. So this was one attempt from us to see how much we can come up with one common metric. And we also try to look for certain aspects that are not covered in the literature. So the way we encountered this challenge was, while we were working on the problem statement, we knew the kind of enterprise code we had and the kind of summaries we were generating. And then we tried to benchmark, try to apply our strategy on some of the benchmark data set. And to our surprise, what we felt was the benchmark data sets are very minuscule and those are very toyish. You can see it from the left-hand side figure here, right? The average number of code lines and tokens is so less. You will not come up with a meaningful study with this powerful LLMs if you are planning to study on those data sets. So that was one wake-up call for us to first look into some good concrete enterprise-grade data set for benchmarking. And apart from that, think hard on the strategy itself. Compared to that, if you see the number of not just the code statements, but even the some of the ground truth code summary that were produced by our SMEs, their length is so much higher than what you generally see from crawled data from public Git. So people might have some documentation written in some good repositories, but even then, the kind of documentation that folks write in enterprise code is so different and so massive, size-wise compared to what you see in public. So this was our motivation. And when we are looking into the literature, like I said, there was a lot of work focusing on the correctness part. But then there is very little work or the other aspects like the verbosity, repetitiveness, the incompleteness of the topics. There are not much work covering it. If you guys are interested in the research topic, this is another one that you can focus on. So this led us to focus on other dimensions. So this is another example that motivated to focus on the other summary dimensions. So here is a summary of this particular class. Okay, you can see it's from a public IBM repository. And then here is a summary of it. The summary is fine, but then there are like three concerns with it. One, you can see that there are at multiple places, same information is repeated in different words. Many of the measures now may not be able to handle them, right? They might not flag it as redundant information. That is one. And the second one is even more challenging. So it gives a lot of this information, but they are not helpful at all. For example, it says like this method is calling that method. Okay. It's very obvious that most of the do post method might be called by the do get method. There's no reason for it to be in the summary. There are these information, right, that are there. It's not right. It's not false, but they are superficial. There's no reason to be there, and it's not helpful, right? So you might not be able to capture them by the current scoring mechanism, but then if you give it to humans and then ask them to rate, they might not accept such kind of summaries. These are some practical challenges that are there. And at the same time, these systems also skipped certain right important and complex public methods. Right, that's like something that may not be acceptable for the end users. So these are some actual concerns that we saw with using some of the latest systems on some enterprise code. So therefore, we introduced a couple of metrics focusing on these aspects. So one was distinctness. So what we felt was like we just expect each sentence to be carrying unique information. So if you try to apply some clustering, then right, ideally you should have right number of sentences as the number of clusters. We know like it may not happen, but it cannot be too less also. Okay, so that was one heuristic that we had. Apart from that, we also try to look into the summary to code to summary ratio. You cannot have like 5-line code having like 6-line, 7-line summary, right? If they don't have enough tokens. So these are some measures that we introduced, and we also try to introduce something around completeness. So what we felt was by doing a lot of interview with some of the SMEs, we learned that if you have some good public methods, and generally when the methods of high cyclomatic complexity, cyclomatic complexity is heavily used to determine the cognitive effort that needs to be put in to understand that code. Okay, generally those kind of methods needs to be summarized for end users to consume them. Okay, so we started to explicitly look for such information in the code, and we try to see if we have a representation of it in the generated summary. So we introduced some heuristics to do it, and we packaged it under this completeness metric. Then to see the effectiveness of this, what we did was we trained a simple support vector regression having human annotations on some summaries ranging between 1 to 10, and we tried to learn the weight of different features. Okay, so what we were able to find was the combination of distinctness and completeness features that we produced, that we introduced, helped to beat some of the baselines that I mentioned, like side, LLM as a judge, etc. And individually also, they were much beneficial compared to some of the other metrics that were introduced in the code summarization literature. So this is another interesting contribution that we made. Okay, so just to conclude, so what we discussed so far is we looked deep dive into the literature of text summary. We looked into some interesting properties of code and how they have been used to do code summaries. And along the way, we looked into the focus on measuring the quality of summary, be it code or text. To conclude, let's just briefly look into some opportunities that we have if you are planning to pursue this summarization research. So I'll broadly categorize in these three focus areas. One is foundational, application, and system. From the foundational angle, if I have to see, right, uh, identifying and mitigating hallucination, I would say, is like one of the very interesting research problems that are happening. So we are able to release some data set, but we can study it in different context and also expand to more languages, but also a way to mitigate them. So that is one research that folks can pursue. Um, LLMs are definitely much better in a long context understanding, but still they still have some limitations, and that has implications, especially if you are trying to do book summary or large report summary. The current LLMs face some challenges. These are some foundational limitations. Different architecture, paradigm change, or some pre-training objectives can help. So that is one thing interesting that we can look into. And like I said, there are no reliable ways to even measure the quality of summary. We still are trying to look into word overlapping metrics or some embeddings, which does not still capture good semantic similarity between the input and the output. So that needs a lot of attention. From application point of view, like adapting it to a very narrow domain or a low resource language is still a challenge. The right Creating that kind of very focused instruction, those data set, right, fine tuning data set is a challenge, and also coming up with all those prompt engineering exercise to come up with meaningful prompts and in context example, it's still a challenge. Okay, so another thing is like how to adapt it to a particular target audience. From application point of view, that's also good, interesting research to focus on. Like one size fits summary may not work, so you might have to adapt to your target person or audience. And finally, there are some interesting opportunities on the system level, like how do you scale up your summarization system to handle large repositories, or reduce the cost of deploying such a summarization system, etc. And folks want more reliable way to realize whether the produced summary is good or not. So explainability of why the model produced some summaries is an interesting research to focus on. And finally, especially in the index setting, focus on multilingual or cross-lingual summarization is very much needed. So not all of us understand English equally well. So if we can have a system that can produce good summaries in the native language, it will be beneficial for the community. So I think here is again a good research opportunity. And there are some students who are already working. So we hope we can do well in this area of focus. Thank you. I think I just finished on time at 5.
Yeah, Srikanth. This was an excellent presentation covering foundations, applications, recent development, your own native work in IBM. Absolutely great work. And the students have been really enlightened. I'm sorry, I was a bit late in joining, but did not miss much actually.
Okay.
Yeah. So
Thank you,
students,
Professor.
please ask questions. Everything is online today. Students.
Yeah. You can also
Yeah,
post me questions. Yeah.
yeah, I had a question. I'm Umukar, so I'm second year student here for MSc. So I had a question that how are longer document summarization approached?
See, first of all, there are two things, right? One, do you want to be focused for a particular user query, or you just want to condense the whole information or not? Right?
Condensation of whole information.
Yeah. So then again, it's just relative. So with LLMs, you will know, right? So we also have this like how much tokens you can consume to produce the output. So you have to be aware of it, and then accordingly try to make sure right you try to pick very diverse set of information to it. So if you have a way to guide them, you can give those detailed instructions. For example, we tend to say like right, if you have an understanding of the topic, then we say like, can you focus on certain topics? As an example, in one of the slides I mentioned, in news article domain, people try to look for those four key aspects: the event, the result, the date, and uh, the event, date, result, and the outcome, right? So then you can try to probe the model to make sure the focus is on those critical aspects, and your output is guaranteed to have them.
Oh, this is helpful. Yeah. Thank you.
Any other question?
Okay. If you guys want, I can make this material available. So I'll share it with Prof and maybe
Yeah,
Hemant.
yeah, that's one thing, Srikanth. So these slides and the recording will be on the course website. Is that okay?
Yeah, definitely. That's fine.
Yeah, so Tosin will be in touch with you for the slides. Yeah.
Okay.
I thought somebody had a question. Okay. So if not, thanks again, Srikanth.
Yeah.
Thanks a lot.
Thanks, Edmund. Thank you.